So this is a topic again on the very high cycle problem, fatigue crack initiation, propagation and failure. And I am coming from the Oku University, which is called University of Natural Resources and Applied Life Sciences. It's a rather small university, state university in Austria, only 7,000 students, and this is mostly concentrated on natural sciences and technical sciences, on biotechnology, on civil engineering, landscaping, and so on. Before this, I have been at the main university, and this topic somehow came from my main university. I will show you then in a minute how it is connected to this main university and how we now proceeded in this field. Besides metals and alloys, we are working on other materials like wood, or bone, natural materials, bio-inspired materials, but this is now a talk on the mechanisms of very high cycle fatigue in metallic material. I think that it could be interesting to you to show you some more experimental methods which we are using, which we have developed, and among these it's mostly the ultrasonic frequency testing technique. We'll go into some details. You asked about this already, and we'll show you how it works, and I will show you some results, not many, and of course we'll touch the question of the frequency influence. Is it high? How high is it existent? And then in the second part of this talk, I want to again come back to the topic which has been emphasized by Professor Mukabe now, which comes from this cooperation. And he showed you the basics, the models, and new results. And I want to show you some more experimental work in this field on the resistance limits, on the endurance limit, and also on the propagation problem in this copper material, in this type 1 material, as it has been named by Professor Mukabe. And I come back to his introduction, very high cycle fatigue behavior of steels, where people assume there is an endurance limit, a fatigue limit, until about 15 years ago, in the range of 10 to the 6, and so and it was assumed, former times we can construct things according to this assumption. But then Japanese researchers found out that there is still failure at much higher numbers of cycles at lower stress amplitudes. And these are these internal failures which have been discussed here now. And this was the very unpleasant situation to deal with. How can we use the data of this fatigue limits now? I will show you also some examples on this, and together with this problem of the fatigue limit goes the problem about fatigue crack propagation. Here you have a typical plot of crack propagation rate versus the cyclic stress intensity, which is stress times root square of A factor. And this is a similar approach. This is the Ferris scheme, where crack growth is according to Mer's law, power law, and then there is some regime at lower stresses where the crack should not propagate, where we have a threshold stress intensity. And this is now also of importance to know the crack propagation behavior here at the, for cracks coming from the surface and for cracks beginning in the interior. And this is the threshold regime which Tanaka, for example, treated. Is the crack growing here, or does it have a threshold case stress intensity or not? So the question is now reduced to this: does the fatigue limit exist, like here, or not? Does the threshold exist in this diagram characterized rate over cyclic stress intensity? And or is there still some crack propagation? We have performed most of our experiments with the ultrasonic testing method, which works at approximately 20,000 Hertz, as shown here. And you see here, up from 10 to the 8th or 10 to the 9th, it becomes very interesting to use this. This is the time which is needed for such an experiment. For example, 10 to the 9th needs 14 hours, whereas with the servo-hydraulic machine you need already 1.7 years. Of course, you can use resonant machines and the new equipment which goes up to 1000 Hertz, but anyhow, this test 10 to the 9 will need here at least 10 days, and you see 10 to the 10 and 10 to the 11 becomes almost impossible to perform with other equipment. So I come back to my university. This is our main old building. The university was founded in 1865 or even earlier. It's not quite sure how we declare this. And this is our new building where we have our institute and where we have further developed this ultrasonic technique, which was first developed, and the idea came in the 1950s from America, Mason, and also at our university, Maine University, in the 1950s it was began to develop this technique, and since about 20 years we have further developed it in our university. So I now want to show you the principles of this. It is a resonance technique using barium titanate crystal, which is working with the piezoelectric effect, and we get axial vibrations, or we also can do it with Gaussian vibrations. In this case, it's axial vibrations, which are then magnified by a booster horn, or it's an amplification horn, and this is made of titanium, and then it's again magnified by such a shape of a specimen. The specimen would be cylindrical, then it is not magnified furthermore. Here you see the displacement amplitude, which is highest at the ends of the specimen and of the transducer, and you see the strain and stress amplitude, which is shifted by 90 degrees, so the maximum of the stress amplitude is in the middle, in the center of the specimen, and we use this distribution of the displacement to measure the amplitudes here or here, and then obtain the strains in the middle of the specimen, which also can be measured by strain gauges. I will show you this. This is our equipment, the photograph. Here's the mechanical part, here's the transducer and the specimen, and here this is magnified again the specimen, and a vibration gauge which measures these vibrations, and this is the electrical part, the power unit, the second one, and you can add 3 more so that you have high enough energy. Process control, the strain gauge, amplifier, and oscilloscope to show the vibration. So the frequency is around 20 kilohertz, and if the specimen end is free, it is a fully reversed loading, which you obtain with this RS-1, so it's tension compression. We have cooled usually the specimens, at least the specimens or the system, with both things, with compressed air, and also we introduced pulses, pulse and pauses, intermittent loading, pulse pause loading, so that we remove the damping heat. Then we obtain room temperature and the temperature that we want to have. And what is important is also that we use the signal of this vibration gauge to control the process, to have a closed loop control, and to have a good and reliable control of the whole thing. So here you see again schematically how it works. This is the ultrasonic transducer, the amplification on the specimen, and a loading frame. In this case, it is shown that we also can fix the second end, so we can superimpose a static load to have mean values of loading larger or smaller than -1. So we have tension preload or compression preloading. And here is shown how we obtain our stresses usually. We measure the displacements, get from this the strain, or we measure directly the strain gauges, and from this we get the stresses, usually just using Hooke's law, multiplying by the modulus of elasticity, and from this we get the cyclic stress intensity by multiplying with square root and so on. So this can be done if there is almost no plastic deformation. Then it is enough to do this, but I will show you then what is going on if we have larger plastic strains. Yeah, I told you already about the cooling necessity, and also we can introduce other environments by putting a chamber around this, corrosion tests or temperature, or we also can perform tests in a vacuum. This is again showing the electric power circuit. They're showing at the screen of our amplitudes, and this is showing the whole pulse, which consists of, in this case, 1,000 cycles. And this is the control signal, which has to be high in the beginning to have a steep increase. So, and this is the slow decay of such a pulse. And we can predetermine these amplitudes and can measure our vibration amplitudes to an accuracy of ±1%, which is quite good. And we can use the frequency also to stop it and experiment if the frequency is changing. This means that there is a crack in it or some other thing which we specify. So this only shortly. The specimens have to have certain lengths and dimensions in order to vibrate in resonance. For broad materials, we use these hourglass-shaped specimens with a smaller diameter. This is increasing the amplitude much more. And for cast alloys, where we want to have big volume, we use this with a cylindrical, and which is constant, has an amplitude or stress across a longer. Thank you very much. A longer distance. These are the specimen shapes for crack growth experiments. There we use usually flat specimens with a notch in it, and we also use tubes with a small hole in it, or be used if we want to superimpose a second load round specimens with a circumferential notch. So that's all possible, and we only have to take care that it still is vibrating resonance. Here you see such a vacuum chamber where the specimen is inside, and this chamber is clamped at the basis of no vibration, and the second part mounted to this pre-load machine. So that's perhaps the essential thing about the ultrasonic technique, and with this technique we can also perform experiments with randomly varying amplitudes, random loaded or two-step tests. This needs only a program, and we did these experiments, and there we again asked the question, is there a fatigue limit, and is there a case threshold value for these applications of varying amplitudes. And now I would like to show you some results. They were asked already. So this is showing you now two types of materials, aluminum alloys and magnesium alloys. I don't say anything about the frequency effect there, but I would like to treat the question about the fatigue limit. We usually know that aluminum alloys do not have a fatigue limit. This is for the 7075 material shown here for the rod material. For gravity die-cast aluminum alloy, again, no fatigue limit. But then, to our surprise, we had a high-pressure die-cast aluminum alloy, which showed the fatigue limit. And the same was with the magnesium alloys. This is the AZ61, so 6% aluminum, less than 1% zinc. And this is the AZ91, 9% aluminum, 1% zinc. Natural die-cast material. And this is the same material, not in vacuum produced, but high-pressure die-cast aluminum alloy, and this showed the fatigue limit. So exactly the same material, once showed no fatigue limit, once showed fatigue limit. Testing conditions were the same, both with the high-cycle fatigue method, and the reasons can be seen in these figures. It's depending on the pores which are introduced during the casting process. If there are more pores, there is a fatigue limit. It's starting with the pores to crack, but there are created cracks which do not propagate. This is the surface of the specimen, and this is the fractured surface area. And after 1 times 10 to the 9 cycles, we observed cracks of 1.2 millimeters which did not crack, which did not propagate. So the material survived. And the same was the case with this magnesium alloy, AZ91, non-produced in vacuum. It showed many pores and non-propagating cracks. And now I come to another material, to the steel AISI 420, which is a chromium steel, turbine plate material, in this case it was 11% chromium, 0.2 carbon. And this material has been fatigued, and we saw that at higher numbers of cycles there were higher values. So, and we observed crack initiation. All these cracks initiated at the surface, because crack initiation below or along the whole time scale, surface cracks, but some did not fail, and they started to grow from the inside at this number of cycles beyond 10 to the 8th. And this reminds us to the plot which has been published quite often by the Japanese people, where they show that the internal cracks may start, may lead to failure even below the fatigue. We did not get this so far, but which have the twofold, which have another lifetime, there they live longer. And I show you the fracture surfaces of this. Here you see, as Professor Mugabe showed you, crack initiation from the surface. Here even a second crack starting from the surface. And this is just this subsurface void, which, or defect, which is the worst one, where the crack started. And this was after about 10 to the 5th cycles. And another photo shows you the internal crack with the fish eye fracture, and after 10 to the 8th cycles it started not from the surface but from the inside. So, and this is the inclusion, which was the origin, and we have analyzed the inclusions, and we found everything in here which could be in aluminum oxide, carbon, calcium oxide, sulfides, and oxides with STATAX analysis. But there are also carbide inclusions, and these could also be the crack starters, where it's subsurface crack initiation, and this steel shows definitely this twofold crack life curves, or lifetime curves. And now the question on the frequency influence. Of course, this is most important. We tested several alloys, and in this case we have tested again this alloy 75, and this was a cooperation, by the way, with Professor Pipan. So we did the experiments at low frequency and the ones at the higher frequency. And what you see, and we are very proud of this, there is almost, not proud, we are happy about this, there is almost no frequency influence. This is the T6 heat condition hardening. This is with, in between cold working. Again, no frequency effect. And this is the third heat treatment, T66, again, no frequency effect. It's the same with the alloy 6061. Again, no frequency effect. And this is a cast alloy, no frequency effect. Okay? But now it comes. Again, no frequency effect with niobium. This, by the way, these tests have been performed in our laboratory altogether. But if we use tantalum, this is an exceptional material with a yield stress, which is below the endurance limit. It's quite interesting. But in this case, obviously, the ductile part of loading is high enough so that there is a big influence. Here you see, this is the measurement with 100 Hertz, and this is with 20 kHz. There is a tremendous frequency influence. So you must know what to do, and I will come back to this again. So now about the frequency effect in our crack growth experiments. There we again tested many alloys, and one example is shown here, the 2024 aluminum alloy, heat staged, okay? And this test was performed in vacuum, and this was tested, these tests were performed in ambient air. And the blue dots here come from the low frequency testing from the 20 Hertz machine. We performed this with a servo hydraulic machine. And the red ones come from our ultrasonic tests. And we performed the experiments at mean values R -1, with full, R approximately 0, and with a tensile overload. What you see here, these very well fit together. There's no frequency effect. There's again no frequency effect, and also here's no frequency effect. If the tests are performed in vacuum, and if this alloy, or these alloys. If the experiments are performed with the same material in humid air, this is R-1 with the ultrasonic method, and this is R-1 with the 20 Hertz machine. There is an influence. The environment influences the result, and we can understand this quite well. The ultrasonic test is much faster, much quicker. There's not so much time to enter the tractive than as with the lower frequency. Therefore, this growth rate is faster at the low frequency, whereas it is lower by a decade or more in the ultrasonic test. If we use other means stresses, the effect becomes less. This is an almost open crack. It's a very high load, and there's not much influence. But we have to take care of course. And what is even interesting, or in addition interesting, is that the threshold values are in all cases the same. Why? The test, the ultrasonic testing is again long enough that the environment can penetrate to the tractive, can enter the material and so on. So that's quite interesting, and we have to consider this, and I have summarized this here. The frequency effect is present at high loads, which are close to the mean stress, of course also in other ductile materials, and if, so that testing damping will be a problem. Polymers and so on, it's a problem to test this. If we are working in a corrosive environment, in all, it would be the same if we consider other time-dependent processes, temperature and so on. So no frequency effect has been considered so far, or has been found so far in most aluminum alloys, in high-strength steels, in titanium alloys, which I did not show here, and in magnesium high-pressure die-cast alloy. So that's what I wanted to tell you in my first part. Yeah, I must look a little bit now. And now I want to come back to the second topic of my talk in copper polycrystalline material. The question of how do persistence lipids, how do these influence drag initiation, drag propagation, and failure. So I show you now this question, not from inclusion and from inside inclusions, but surface-induced PSPs, maybe also inside, we don't know, and how do they influence the failure in this material. For this, we used electrolytic copper, 9.9, and used both specimen shapes, which I showed you already, and mean grain size was 60 micrometers. We polished it, did first mechanically and then electrolytically, so that low compressive loads were introduced and calibrated the whole very carefully. So, and the main thing is that this is a strain control experiments, so we measure strain with the strains, and it is controlled via these strains or displacement amplitudes, and therefore the test first has to be calibrated to obtain and measure plastic strain amplitudes, which cannot be measured directly. To determine this is rather a long process, and then we perform the experiment with a rank loading procedure. So we didn't raise the stress immediately, but rank loaded it as it has been done in former experiments in the past, so that we could somehow compare the tests. So this is, in short, CPK, this ramp loading, and after we have done this calibration procedure here at several steps, then the test was run at defined constant total strain amplitudes. And as I pointed out, we have to consider now these plastic strains, which are here of importance and which we have measured with different methods, measuring temperature. If you are interested, I can show you or can tell you afterwards the details of these measurements. And in order to obtain the stresses, we have to subtract this plastic strain amplitudes from the measured total strain amplitude, and then get the stresses as being valid for this measurements. And I come to the results. This carbon told you already. There are persistent slip bands formed. These persistent slip bands have been defined in the past as such slip bands which come again after polishing the specimens and reloading them with the same load. And if they appear, these slip bands, surface features as slip bands, if they appear again, then they are persistent slip bands. Indeed, we found these at an amplitude of approximately 63 megapascals, which is slightly higher than the low frequency amplitude 56, as it has been determined by Professor Propagatio in the past. There are also indicated as the plastic strain amplitudes, but I don't have enough time to explain this too. So the conventional PSP threshold was found at 63 megapascals, but we then tried to find out, do they form at lower stress amplitudes or not? And indeed, we found, and this has been shown by Professor Mugabe, there exists also PSPs, and they are formed even at lower amplitudes. And so far, we found them down to an amplitude of 45 megapascals. Again, after polishing, they showed up again. So, these features are how we first identified or thought these must be PSPs. At the surface, seen with the scanning microscope, there are extrusions which become broader and longer with time. This is the number of cycles. It was below the PSP threshold, and continuing the test, we always have to interrupt, go to the scanning microscope, have to find the same place again. We find these again becoming more and deeper. I will show you also our measurements, and more frequent. So in this plot, we have now characterized the amplitudes depending on the number of cycles where the first PSPs appear. This 63 would be the conventional PSP limit, but at lower amplitudes like 55, 10 to the 7 cycles are needed, at 10 to the 8, at 45, more than 10 to the 8 cycles. So this is the limit which we found so far, but probably we can find also values at an even lower stress. So we call this now the very high cycle fatigue PSP threshold, but maybe it's even lower than 45 megapascals. And here you see the dependence for example, the 59 megapascals, which I showed you just now, on time. This is the number of cycles, and the percentage of grains which show PSPs. So after, for example, only 10 to the 3 times 10 to the 6, there are only 2% of grains covered with PSPs, and raising the time of loading up to 2 times 10 to the 9, 40% of all grains are covered by PSPs already. And we can do this, and we did it at lower amplitudes too. And now about the profiles of these PSPs. Professor Ravi pointed out that there are different methods. We see here a PSP which was formed slightly below the PSP threshold after 5.10 to the 7 cycles and after 5.10 to the 8 cycles. If we make roughness measurements across this with different methods, then we get a profile of this PSP. So one method is to use the SEM to tilt the specimen and to use such a program, MEX 3D profile analysis software. Then we obtain the following features of this specimen surface. After the 5.10 to the 7 cycles, we get this profile with mean heights of approximately 112 nanometers. We can also determine RMS values, mean square values, which are a little higher. And after 5 times 10 to the 8, this becomes more higher and more pronounced. The mean height is then 164 nanometers. So this fits quite well the measurements which have been performed in Erlangen and have been done with the SEM. We also did the same with the AFM, with the topometric explorer with a pyramid of 50 grade, and we also used another tip which was even more slim, and this is the profile in this place of the PSP and here in this place, where we thought this could be a microcrack already. And you see, here it is an extrusion which is mainly measured, and here it is an intrusion in this place. So that's the second possibility to measure the profile and the roughness of this measure of these surfaces. And as a third method, we used the plastic replica technique because we were not quite sure if our pyramid in the AFM was not steep enough to penetrate into it. So we did this plastic replica technique, used this, which is a plastic which is made soft by acetone, which is pressed to the surface, and which then gives the profile. And this inverse profile is then viewed in the scanning microscope. And this is the original surface, and what is going in here is coming up here. So this is an extrusion. And the results of the measurements across these fields are shown in the next slide. And you see quite impressively, here's the intrusion, here's the extrusion then, and the profile. And by this direct scanning electron microscopy measurements, we obtained almost the same results as with the replica technique, which was quite convincing for us that we did a useful measurement. So these are the three methods how to determine the profile of to determine the surface roughness of some specimen which has been used by us, and which could, of course, be improved by using an AFM with a thinner pyramid, which we did. So the main result is summarized here. Approximately these mean roughnesses and these stresses at the surface and minima and maxima here, you say they vary very much. Of course, we have deeper and less deeper intrusions and extrusions, but if we do enough statistics, and we did this, then I think these values are not so bad. So, and now about the dislocation structure of these persistent slip bands. This is another feature which is characteristic of fatigue loading in this regime. We find dislocation clusters and cells. We also wanted to find ladder structure. We did not really find it because these are polycrystals which are randomly oriented, and the cut was not in this direction, so we did not find this, but these are typical features for loading in the PSP regime. Next question was, of course, now about the fatigue life of these polycrystalline material. And here's plotted the Wöhler curve, stresses versus number of strains. And you see here the fatigue life is much higher than the stress at where the PSPs were formed. These are the first PSPs coming up, and this is the stress for failure. And this is the specimen which failed at 1.129 cycles, which was investigated in detail by Professor Mudrabi, and we find this rather big difference and wanted to know what is the reason for this. So the dislocation structure also was quite interested. Professor Mudrabi pointed to this lamella-like structure, which was indeed found also in our TAM studies, and were pronounced thin lamellas, which look even like small angle grain boundaries at the fatigue limit. So, and this summarizes now just the stresses, the strains are given here, the plastic strains and the total strains. The conventional PSP threshold is 63, the very high cycle threshold below this at a higher number of cycles, and the fatigue limit at a higher stress. And therefore we now ask how can we explain this difference, and for this use fracture mechanics principles. We determine the threshold stress intensity for crack growth, because somehow I thought it could be correlated with non-propagating cracks. So for this we used our specimens, which are flat specimens with a single edge notch, and we used optical measurement of the crack propagation along this specimen with, here you see, with an optics which is magnifying this area by 250 at the screen, so we can see how the crack propagates and measure this directly. Of course, there are other techniques also possible. We use this technique as being the most reliable. What you see, you believe better than what you can measure and do not know what is happening. So, with this procedure, we used fracture mechanical calculations of the stress intensity factor using epsilon, the total strain amplitude times E modulus times the crack growth length and correction factor. If this is done, we get this crack growth curve, crack propagation versus Kmax. Here's only plotted the tensile part of protein Kmax. And you find, we tested it with 3 specimens, we find crack growth rates below the theoretical threshold value if you assume that one Lewis vector or one atomic scale distance is covered during one cycle. But obviously there is still crack growth below this, and these values are sometimes considered also as threshold values, but you see they are quite different. A real threshold value is this one, where we have used 10 to the 9 cycles and only had a crack growth rate, and then at last of 10, no crack growth rate at this theoretical value of 10 to the minus 14 meter per cycle. So the last one, which grew, was here 10 to the minus 30 meter per cycles and so on. And now the question is, how low is this? This is about 3.4 megapascals per meter in this crack growth range. For the other specimens, it was a little higher this year and this year. And now the question was, how does this correlate with the fatigue limit? To do this, it is usual in technology to use the so-called Kitagawa diagram. The Kitagawa diagram shows you the stress versus the crack length. This is the crack length in a logarithmic scale, also the stress, and there is introduced here our endurance limit, which is 93. And there is now plotted the stress of our crack growth rate curve, where the stress intensity was 3.4 megapascals per meter. Here's the stress of the second specimen. This is the second threshold, and this is the third threshold. If there's plotted this line, which is an inverse power of 2, because sigma is, and k are proportional to the square root of meter, so it's half slope. If we prolong this, if we draw a line here and come to shorter cracks, we meet the endurance limit at a crack length of approximately 0.34 millimeters. This would be the limiting crack size where crack propagation obviously is possible. Here's the threshold. If it would be shorter, it cannot grow. This is according to the equation delta sigma, delta k is delta sigma times square root theta. We also introduced it for the other thresholds, then it becomes a little longer, and for a third threshold area, which is here, which is higher, and there we obtain non-propagating cracks, obviously cracks which are then the limit for the long cracks which can grow. So we can say longer short cracks grow, but the shorter ones do not grow. And indeed, we have found that, for example, at 87, the non-propagating cracks are in this case about 100 micrometer or 150 micrometers, and Professor Mugabe showed you very impressively that there are short cracks in the range of not more than 20 micrometers for 63 megapascals, which is the conventional ESP threshold. So, and at 93, the crack or the notch has to be at least 345 micrometers, which is more than a decade longer, in order to propagate this crack. So obviously, at the threshold value, the stress is not high enough to be able to propagate this crack. So this is a crack growth problem, obviously, in this material, in this electrolytic copper, and we may understand this by these measurements. And to summarize what is going on until failure, we can say first, slip bands are formed. Then, if the number of cycles is high enough, persistent slip bands, first slip band, fusion slip bands, which are not persistent. If we go on cycling with higher numbers of cycles, they become persistent ones. Intrusions are built up. They become deeper and more frequent with increasing number of cycles. And now we have to differ below the endurance limit. There are formed below the endurance limit, but above the ESP threshold. Many non-propagating cracks are formed, small cracks. They, in addition, lead to stress relaxation of the volume. I say this because we saw this in the experiment, frequency was changing. And the crack is not a fatal crack. But if the stress or stress intensity is high enough, then we obtain long and propagating cracks and finally failure. So that's, I think, the end of what I wanted to tell you. I summarize again. I showed something about the ultrasonic testing technique, which is very effective in the very high cycle fatigue regime. It may be the only possibility to test such failures which occur, for example, also in offshore structures. After 30 years, you can compress these tests into few days or months. This is the longest which we do usually. We can measure these SN curves, which are very important today in the very high cycle fatigue regime. We can use the same technique for measuring the thresholds for crack propagation. And it's interesting to say that there's, in many cases, no frequency effect for most technical alloys, obviously because the plastic amplitudes are so small that we can neglect them. But there is a frequency influence, of course, at higher amplitudes, above the delta K threshold value in corrosive environment, and at the threshold is sometimes no influence. So now the results in polycrystalline copper. We detected this information which is dependent not only on the stress but also on the number of cycles, and can these PSPs can be formed also at lower stresses than assumed until now. The endurance limit for this material is higher than the PSP threshold, and we try to explain this by saying that these are non-propagating short cracks using the Kitagawa diagram, which is quite usually used in technology considerations to correlate the behavior of the whole fatigue life with the crack propagation life. So, thank you for your attention.